stuck a little bit. It's time to do something. What about time-dependent protection? Who they are and why? So, good morning, and let's continue our course. What's for today? Time-dependent protection. What is this? We will continue with overcurrent protection. Where the problem starts. Let's say you have an asynchronous machine. How in Russian it looks like? Time, current. Something like this. If this is nominal current, the rated current of the machine, this one will be 3, 5, 7 times higher. What kind of protection would you like for this machine? On the one hand, it should disconnect machine, this motor, in case of internal fault. It's clear, but that's not all. You also would like to protect it from overload damage. It is possible it cannot start, I don't know, something struck. Or one of the way to damage this machine is to attempt to start it with lower voltage lower than rated. So it will not produce rated torque and will not start. Starting torque. What should we think? Actually, we need a kind of protection reflecting thermal, let's say, thermal capability of this motor. It should allow high current for the short time, but it should disconnect machine in case the starting regime, how to say, is prolonged. It takes too long to start. In general, you will think about something like from 0 to time of E squared. Or something reacting to summing E squared time. Something reflecting thermal effect of the current. It's what you may start to think or keeping in mind overload capability of your asynchronous motor. What can it be? The idea came with relays like this. Like this one, or maybe I have maybe it's my relay. Or some. You may think about something. This small circuit breaker is equipment with this area. 1 second, I know which shelf it is. I know where to look. Oh no, it's foreign capacitor. So, done on it. Where is my... Oh no. Everything looked for. It's a heater. See this spiral around. And so-called bimetallic plate. Take a plate combined of two metal with different thermal expansion rate. When it's cold, it's flame. But if you heat it, it's a heat. If you take lower metal with a high expansion rate, it will bend like this. This can be used, so in combination with, you see, it's a heater around the plate. When heated, it will bend and trigger the switch. This is how something with thermal energy can be created. It's a way to create something with thermal energy. But of course, it's good, but not so good. It's not precise. The problem with thermal relays, they are very imprecise. Tree current is dependent on ambient temperature, and that's not all. With the time they lose their capacity and their characteristics. They are not best solution. Next idea, via thermal relays are still widely used on low voltage circuit breakers. Do I have a thermal part here? No, it's blocked. Oh. No, this one. Yeah. This is circuit breaker for 300 amps, something like this. Here they are. I can close. Here they are thermal elements. You will find them on low voltage breakers. Here, for example, this old one. Here they are paired, 1 and 2. You will find them, but for higher voltage, the imprecision makes them unreliable. What's done next? What dominated, how to say, the market for a long time, things like this. It's called induction relay. I will open it. So, here is, oh, I need to go this way. What's in? It's a, here I'm a coil, let's see. You can select start current with this switch, with this plug. This coil, I need to turn. This magnetic system, it's so-called screened will sit the current coil. Key idea was at the end of the pole, it has a conductive copper, like this. It's a conductive copper grain. So magnetic flux, common magnetic flux will split in two and in one, and flux coming through this copper ring will be delayed. Similar system. This one will be delayed. Similar. Something very. Similar we can find in small asynchronous motors. Here it is screened. This one in the fun. Here is a conductive ring covering part. Here it's how to say shadows or screens part of magnetic flux. This makes this flux because current will circulate in the ring. Here will be current, and this current will produce its own magnetic flux. So actual inductance of the ring will delay magnetic flux through this part of the pole. When two magnetic flux came through conductive disk or barrel, rotation, torque. What? Torque will emerge, and this, where am I? Here. Disk will rotate. When current flows through the coil, this rotates. Induction. Idea of this induction relays. Next, interesting thing, if you see the disk sits on the swinging arm, on the small current it will rotate, but nothing will happen. When current exceeds no limit, it will. I hope you can see. Disk will come in junction with this toothed arm, lift it up, and send a disconnection signal. So this relay will have characteristic current time like this until arm is connected to the disk. Time will be infinite. It will simply rotate without any effort. At something like 1.2 I plug, arm will swing. The toothed sector will come into junction with the rotating spindle, and you will get characteristic like this, going to zero. Time-dependent characteristic. The higher current, the faster disk rotates, and in shorter time, trip signal will be sent. Exactly this relays is more complex, this type of relays. They also have second arm. The magnetic system has 3 legs. One screen and swinging arm like this. Coil is in the middle, the current flows. And here is the disk. While currents are relatively small, only this part works. And this rotates, counting time. But on high currents, this part triggers instantly. Cause instant operation with this adjustment screw. You can select an instant trip time. For this one, if it's set, so for mine, this will be something like 2.4 amps, because it's plug set 2 amps. And this and here approximately 16-20 amps will be trigger time. It's 8-10 times. When it's triggered instantly. What do we see in front of us? Actually, it's a base for 2 zones protection where one zone is instant for line faults and another one works as time dependent, or you can use it as protection to your asynchronous machine. This overcurrent zone operates in case of short circuit, and time dependent will work as a overload protection, OLP, overload protection. Kind of, in general, it should it's protection integrating thermal effect. Now, where we are? Let's say we have a distribution network. Source here from the bus came, from our bus came one of the distribution line. What we will see? High voltage fuse, transformer, at a 0.4 here, 0.4 kilowatt client bus. What kind of characteristic will have the circuit breaker? Thermal and instant. Another fuse. Let's say we have a fuse protection here. Again, customers. What kind of characteristic will have this fuse? Here is characteristic of our circuit breaker. Here, what we will see? Something like this. With 20%. What can be else? Maybe we have a richer customer with its own protection device on a middle voltage side. What kind of characteristic will have it? It should somehow coordinate with this circuit breaker, yeah? The circuit breaker, thermal, instant. So here, 100%, we will see something like two coordinated zones. Maybe in all the time relays with pneumatic chamber were popular in some manufacturers very loved relays with pneumatic chamber. It has a chamber piston and calibrated kind of nozzle. On small currents, this chamber collapses slowly. On high current, the higher current, higher is pressure, higher is the air flowing out speed. In fact, unreliable thing. Really unreliable. With time, these tiny nozzles have tendency to be clogged out. So relays fail. Also, strangely, with time, oil from they usually came in a set with the oil switch. With time, it's observed, strangely how it happened, but oil got into these chambers. You open it and it's oil inside. And this oil, in summertime, relays operate smoothly. In wintertime, oil freezes, not like ice, but it's more viscous. And the relay fails. Useless thing. Use digital. Don't waste your time, put a digital. Digital will work fine. But what kind of characteristics should they have? Correct answer. We need to coordinate with customer overcurrent protection and overload protection. We need to coordinate. If we have large customer, like for example water treatment plant, they have large, usually 6 kilowatts, large pump motors. They will have this overload protection characteristic. And we need to coordinate with fuse. One of the moments, see, it's strange. I'm pointing with arrow to 0,4. And what about this fuse? What about this fuse? Why I'm not pointing on it? There is not a well news. On the one side, managers of network, they try to save money. These fuses are inexpensive and, in some degree, they are reliable. But they stand outside, even new, they have quite widespread of characteristics. Because long arc, the higher voltage, the longer arc, and less reliable characteristic. That's not all. They stand outside, they all are open mount. You can see them on the poles. Even in cities, they stand in chambers, not heated, not dry. They are open to elements. Okay, they are protected from direct rain, but they are not protecting from the morning mist. I saw this in person. In time, such fuse can suck and humidity inside. Can take water in. This means what it will during the fault it will operate, but it operates with delay. That's why I'm not pointing an arrow on this fuse. These fuses are not reliable. Believe me. More of that. Also, experience. If such fuse burns, net guys do have a very bad habit. They put not what needed, but what they have with them. Often. Nothing unique. When instead of 25 amps fuse, you will find 250. Because they just had it with them. Linemans are limited in time. Company bosses want them to take care about about everything in short time, do it faster. They don't have time to go to the base, take fuse, come back. Okay, we will put what we have now to reduce customer disconnection time. Because bonuses are calculated, how? Number of, you should be inside KPI, and your KPI is number of clients multiplied by discontinuing time. Yeah? Do it faster. These fuses are not reliable. Watch what's on 04. When you need to coordinate, your first target should be largest of the clients. In best case, your protection should take all this, should act as a backup protection for all these buses, for this bus, for all buses on customer side. It is not an excuse. Where is the, let's say, border between your company and customer? Maybe here. Typical here. Maybe transformer. Maybe here. In our reality, for most of the customer, our border is after the metering current transformers. We switch fuse or block fuse, current transformers after the current transformers. The bus belongs to customer. But customers exist. Here is the border for larger customer. Borderline, anyway. This fuse may be on the customer side. No, this is not excuse. Watch at this. You need to coordinate with this fuse. Start from the most power client and go down. In ideal case, you will be able to protect all. But in our climate, it's unrealistic because on the one line we can have 1 megawatt customer and 100 kilowatt customer. Source, line, transformer, breaker goes down. In flat independent scale, we would have something like this. A1, A2, A3. It's a flat current independent, time independent scheme. For dependent scheme, last protection zone should become like this. To reflect this is character. I can show time, current change as a virtual length of the line. Here I'm drawing in coordinates. Time, imaginary distance. This distance is imaginary. I'm reflecting current change as a distance of some line going into the customer. B1, B2. This also will become, if good, time dependent. Maybe even like this. solution to the problem of this inrush characteristic and overload and necessity to coordinate with fuse and low voltage circuit breaker with thermal protection, even digital, yes, you can find modern digital, you may face who's calling and why. Yeah, close. Yeah. Он студент, да. Ну видишь, не песует там вкус. Который занял стажировку, а Димса должен Okay, where am I? It's for the people are wondering about next lecture, but it's not our. What's our? Our problem, Nova Day 04 circuit breakers may come with the characteristic like this, not rounded thermal. But from straight line, it's a digital created from straight lines. Nothing in reality, nothing changes. Anyway, we can approximate it with the characteristic like this. We only need this time depends. Now, what you need, if you, for example, it's current time chart, you have a few, for example, it's a fuse, yeah. Here is the characteristic of the fuse. Fuse, come here. See this nice guy? 1000 ohm fuse. here. It was marked 1000. It's on client side. What you doing with your protection? First, you need at last two zones. So fuse characteristic, I need to, here is, it's approximately this, when it goes straight, this point is approximately 1.2 kiloampere for my fuse. What will be characteristic on 10 kilovolt? 1.2 multiplied by 0.4 divided by 10. Why I'm doing it? Because I'm calculating on distribution network. I started from example for my network is 10 kV. 10, 11. If your network 11, put 11 here. If your network is 24, put 24 here. We need to reduce characteristic to one current base or one common current. Okay, here is a characteristic of our fuse. Yeah? How will we coordinate? What we have? Source, switch, fuse we actually ignoring. This one, 1000 amp fuse, and here is 04 customers. This line is a chart, operation chart of this fuse. What kind of characteristic do we need for our protection? This is our protection. We need to protect line, yeah? And we need to coordinate with fuse because we need a backup. All our protection zone should end at last here. We need to protect all this. Meaning, we will have two zones. One will be instant. A1 instant zone. It's determined, its straight current is, this point is 1.1 roughly multiplied by fault current number 1. It's three phase fault at the next bus. Here is the trip current of my instant zone. Next, maybe I beat to finish somewhere here. What will be next in simplest case? In simplest case, my second zone will be like this, time dependent, is A2. This will cover, what it will cover? A1 will end somewhere here. This what A2 will do. And also A2 will act as a backup protection for the transformer. It will be sensitive to fault on this bus. More sensitive. With the digital relay, I can, very typical for digital relays, they are able to create, they offer us 5 zones, up to 5 zones. And the last one, time dependent. Here, for this zone, maybe to make it more visible, I will draw a bit like this. I create, actually this step is not needed. I draw it to make it visible. here is trip time 1.1 square multiplied by current number 2. It's a fold at the end of next line, or maybe you can take this fold reduced. And last zone, A3. For these two zones, time is constant. For this zone, time is a function of current. It's time dependent. The higher current, the faster it's trip. Some guys may try to do all the job with only one time dependent. I saw it in Brazilian papers. No, it's not a good idea. You can do it, but it's far from performance standards. It's not a good idea. If you have a relay with 5 on your disposal are 5 zones, why try to cover all with the one? Anyway, you paid for relay. You don't need to pay for each zone separately. See, I can try to get the same with flat zones, independent. I can try to create something like hop, 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 and hop. I can try to create this approximation, but all the difference see, all this difference is a negative impact of the fault current. It's not needed. All these gaps means what fault current will burn your equipment. No, it's madness. It's useless. Time-dependent characteristic is what coordinate as well with fuse, with low voltage circuit breakers, and so on. Now, bit about creation of this characteristic. Characteristic like this. What it has? Start current. Yeah. It has time, and somehow we need to set the curvature. Yeah. How it bends. Actual industry relies on one standard. It's a British 142. One second. It's a So, BS142, all also can be reflected as in ASC 60255. In its, if I know, in its section 3. So idea, trip time in seconds can be expressed as a time multiplier multiplied by beta constant. This one, k, is a time multiplier, beta is standard defined, current related to, it's a set current. Well, okay, is reference yesterdays. Or maybe, I can do like this. It should be in power of alpha minus 1. So here, alpha and beta, two constants. K is a time multiplier, and this is set current, or sometimes they call it plug current. For this old relays, you had a current plug, set defining what? Is your characteristic current time. This start current when it starts. In older relays, there was a special current plug. You need to. This one for this model, it was screwed in to make contact safe. For new, of course, it's just a digital constant. So standard defines 4 characteristic type. Normal inverse, inverse, very inverse, extremely inverse, and long time inverse. Inverse, inverse, inverse. So alpha and beta, these constants are specified for each time of characteristics. For normal inverse, it's 200 for alpha and 1400 for beta. Here should be 1 and 14 and 1 half. Two and 80 and 1 and 120. Here are four base characteristics. Depending on what kind of fuses and what kind of circuit breakers you deal with, select one of them. Old school, you know what people are doing? They're drawing them on kind of transparent material, like PMMA or semi-transparent paper. Just draw this charts of characteristics, and apply them to factory supply chart of equipment. I cannot tell which one will work better for your case, because you need to take into your hand to get it from the customer. Maybe customer will tell you, oh, I don't know, it's something. Ask for photos of main switch on their panel, or main fuse on their panel, and find this manufacturer or something similar. Then you will be able to create this tail of your characteristics. Maybe for all the kind of equipment, if they these characteristics are for newer relays. For very old kind of equipment, you may face a special type of characteristic. It's called Ri. Ri characteristic is to match all this aluminum disc relays, induction relays, to match with the induction type of relays. Most case, you are aligning to the customer substation. So substation is not yours, substation belongs to customer. You aligning to the 10 kilo switch. It most possible it's problem what you have a customer. Here is induction type of relay, and here is your border. You cannot ask them to change protection here. They have induction type of relay, so you need to align. Customer may listen to you, may not. If customer not listen, use Ri type of characteristic. The trip time in second is time multiplier divided by 0.339 minus 0.236. Here should be current divided by set. Yeah. It's Ri. Should be divided by. Yeah, should be divided by. It's okay. Also exist. You can find in your relay description XIG, special type of characteristic. This characteristic is not suitable for line faults. It's for earth fault protection. XIG type of characteristic created for earth fault protection. It's for do not use it for overcurrent protection. Okay, if needed, it has trip time 5.8 minus 135 logarithm current divided by Ki3. Natural 131. It should be 135, sorry. Not 9, 135. XIG is for faults, do not use it for line-to-line faults. One question is about safety zones. This one moment with the safety zones. Standard arrows to widen error zones. Be careful. For very typical saying, oh, we have 10% error. And that's all. Actual standards allows this extension. So if accuracy is epsilon, I by I3, 2, 5, 7, 10, 20. Allowed tolerance for normal inverse will be 2.25 epsilon 114, not specified, for 10 times 101 and 1. You see? Standards allows lower tolerance at a small current. So be careful to provide sufficient margin. If you coordinate two relatives. If you coordinate with fuse, remember what tolerance of fuse is 20%. Tolerance of ordinary circuit breaker also somewhere around 12%. So safety margin should be 20%, not 10. If you coordinate relays on a small currents, tolerance margin more than double. The same for very inverse. 244 epsilon, 126 epsilon. Not specified, again 111. And for long time, for long time, 244 epsilon, 126, 1. Not specified, not specified. Here are tolerance margins. Actually, standard allows to operate without tolerance. Just for knowledge, Fxig looks like this. Also, some manufacturers determine also return time. Time when relay returns to its initial condition. It's done with purpose. This type of relays, they are lazy to return. It's done with purpose because overload may not be constant, may up, down, up, down, up, down. So these relays are lazy to return. They well designed, they return with delay. And this delay this delay is determined. What I'm doing? It's a reset time. It's a current, may come with current multiplier. Okay, same case. Multiplied by reset time characteristic to E plus I squared minus 1. TR for our characteristics. 9.7, 43.2, 58.2, and 1/2. The reset time in second for our characteristics. Well, these relays are lazy. Modern versions are equipped with lazy return time. I need to take a word on special occasion. Special occasion. What kind of special occasion? Special occasion is, come on. Special occasion is a network of the power plant. For network of the power plant, you have, let's say, main transformer connection to net. You may have some transformer with your generator, and this tiny thing, self-supply transformer. Here, this very possible will be 6.3 kilovolt bus self-supply transformer with multiple multiple load. One is very large asynchronous machine. It's a water pump supplying the main boiler. And other are much smaller. I need to draw it in red. For this switch, you will see a problem. Because of very high load current and start current of this motor, you will be in serious problem creating protection for other clients, smaller. But you need to protect this line. The switches are not very reliable. And here will be problem. High current of main pumps makes, if you create protection like simple flat scheme, makes it insensitive. What to do? The idea, solution to this problem is a creation of two protection sets. One set operates on three-phase fault, and it's typical. But another one, since most faults are not symmetrical, even three-phase fault, in case, how can three-phase fault be created? Your personal left earthing knife and put the line under voltage. It's a personal error. No switch in this world connects the poles simultaneously. First two will come in connection first, so at the first moment you will see line-to-line fault turning into three-phase. Even if it's earthing or knife or this earthing ring left after repair work. So, special scheme of protection used in, may be used in such case. This special scheme includes, here is your current, special, it's overcurrent relay for the first zone, it's for the second, okay, this one will be for the second, this one will be for the first, very good. Next element. This is fine, but the next element in all directions, negative sequence voltage relay is used. It's done by voltage because old negative current relays are unreliable. For modern, you can have negative sequence current relay. Do you know what negative sequence is? What's your knowledge in symmetrical components? Fortescue transformation and things like this. Oops. What about Fortescue transformation? Symmetrical components. Any knowledge? No. I'm afraid I'll need to take care about it. So its idea, basic idea, what real non-symmetric polyphase network can be decomposed into set of symmetrical network. One for free phase there will be three network. One with direct rotation, one with opposite rotation, and one zero sequence, not rotating at all. So these two are operated on the basis of negative sequence component. Any of them will activate. So instant works fine. Only in case we have negative sequence. While this is done, load current, startup current of the asynchronous motor is symmetric. It will not contain negative sequence. Fault current is not symmetric. You have line-to-line fault. So in case of fault, this relay will trip and will allow you to operate this thing like there is no load current, pure on fault, calculated pure on fault regimes. Characteristic. So this is enable signal, and of course you need, this is enable, this is current. This will calculate you a trip time. Trip signal. This is fine, but maybe one more thing. In this scheme, under voltage protection may be incorporated also. To make this system working fine, even on three-phase fault, element direct sequence voltage lower can be incorporated and also activate under voltage protection element can be used also for additional safety. But key moment to make your protection sensitive in such case, it's a very typical for thermal power plants, where high load currents of the water supply pumps, air supply fans, fume extraction fans, they are high power, but most water supply of the boiler. 2, 4, 6, I saw 6.5 megawatt pump in person. 6.5 megawatts in one piece. Consumption of the city in one piece. Six of such supplied 800 megawatt machine. No, 2. Yeah, 6 supplied 800 megawatt machine. So 3, here to avoid low sensitivity, unsymmetric sensor is used. Time-dependent characteristic. It's the weight return. Current over. Sorry, what I'm doing. Negative sequence current is greater. Time-dependent characteristic. Yeah, one thing about terminology. I forgot one thing. Name for this current. Sorry, I forgot. At the moment when toothed sector is in junction with the screw, it always picks up. So some manufacturers called the starting current not a start current but pickup current. Problem boy. One sharp X and problem solved. What I forgot? I named characteristics. So key idea, when you create a protection for distribution network, it is better to make a multi-stage and last stage to coordinate well with fuses and thermal. For example, thermal, how to say, relay equipment, low voltage circuit breaker, it's better to use time-dependent characteristic. It's a good solution. Okay, I think it's enough for today. Maybe some questions? Who has questions? No questions.